Hello everyone, today I'd like to share my CUDA programming project, GPU-accelerated Dynamic-GNN model for traffic flow prediction system. This ended up a bit different from my original plan. I spent roughly 60% of my effort on data processing and 40% on model training. Usually in similar projects, someone else has already cleaned and packaged the dataset, and we only tweak the model. This time I choose the PIMS data for LA, like 4,888 sensors, reporting every 5 minutes from January the 1st to April the 27th, 2025, totaling over 160 million rows, although it updates daily, but it isn't maintained by a dedicated team. So there are many missing or anomalous values that require large-scale cleanup from. I took this opportunity to dive into parallel data processing and GPU acceleration. At one point, I even considered switching this project to sensor anomaly detection. Honestly, I learned a tremendous amount. My day-to-day work is usually CPU-based, only using GPUs for images. So this was my first foray mission in GPU computing and CUDA programming. I focused on implementation and performance optimization rather than training the model's hyperparameters. Those tasks aren't as closely related to CUDA programming. But even beyond CUDA, I made many new discoveries that I'm excited to share. And this presentation is in two parts: data processing pipeline and model training. First, let me introduce the PIMS data, which underlies most of this work. A performance measurement system is maintained by Caltrans and includes thousands of loop detectors across California's highway network. Its data span many years, enabling multi-year comparisons. Public downloads only cover the current year, from January the 1st to today. I've emailed them requesting a full-year archive but haven't received a response yet. We choose District 07, which means LA, because it has the highest data quality and is popular among researchers. We use 5-minute station data. It's ideal for flow prediction and moderate insights. By contrast, 30-per-second data exceed 700 MB per day, while 5-minute data are only about 170 MB per day, which fits our resources. And our core observed metrics are as below: flow, occupancy, and speed. But other station metadata serve as reference features and play a crucial role in preprocessing, like location, highway number, milepost, and road tab. And we also use station metadata, which contains static information for 4,888 stations, but 4,883 with coordinates that naturally forms a graph for a GNN model instead of the time series model I originally imaged. This was also a challenge, as I had never worked with GNN before, so I pushed myself in a new direction. Similarly, PIMS provides sensor health data, but its accuracy seems questionable. We will put it to a good use later in masking. And in data processing, the main steps are integration, masking, and interpolation. First is raw data preparation, and there's a very start of the project. Next, we pull weather features using the Meteo State Overlay API for coarse spatial temporal weather data, map grids to stations via KD tree, then resemble and interpolate overlay weather to 5-minute intervals, and finally output the merged data table. And in this part, I've tried GPU acceleration like multi-threading with job-lab parallel and desk for multi-core parallelism and CoolML, but it doesn't seem to work. because the real bottleneck as network I/O and the GPU can't accelerate it. And next, we merge external features. First merge vector into each flow record, then a label features. I use sine cosine transforms to better capture cyclic patterns, and finally export the cleaned dataset. Well, the trickiest part of processing is masking, which I divided into 3 masks: health value mask, rule-based logic mask, and the Mahalanobis distance mask. I will introduce each in turn. The first, health value mask, using a predefined health score threshold from PIM's quality table. The table marks each day's sensors as good or bad, but it's hard to download and not very precise. Good or bad flags don't cover all stations and sometimes overlap oddly, like from some internal algorithm. So I only pulled 7 days of daily health slice reports. Based on those health flags, I computed a daily health score via an exponential decay model, like half-life, and used the GPU CUDA to massively speed up the half-life grid search and the final score computation that gave a rich, fine-grained wave of sensor health. And the steps for the health value masks, like first, exponential decay smoothing. We use event scoring and the decay weights, and the weighted average. And then for the grid search optimization of the half-life parameter, we use MSE mid, MSE exter, and combined loss. And finally, we select the age. So GPU acceleration matters because summing hundreds of days per station on CPU is a nested loop. CUDA broadcasts matrix operations in GPU memory in one go, speeding up tens to hundreds of times. And next, we use the rule-based logic mask. We applied common sense rules on speed thresholds, minimum sample counts, and sudden zero flow specs to flag bad data. Totally like speed anomaly and low samples and zero flow specs. So we linearly combine these 3 rows with weights and compare to threshold exceeding 8 marks and anomaly. To pick the threshold, we repeatedly test on labeled data to optimize the combined time level and the day level I1 score, like the coarse grid and the fine grid. That yields a fine-grained mask that fits daily slices and time level anomalies. And this step of logic mask doesn't use GPU, so we accelerated grid search on CPU with pandas and the job lab to do some parallel computation. And about the Mahalanobis mask, it's a multi-dimensional outlier detector. It measures how far each record vector divides from the distribution of its type group. In this part, like holiday, event, weekend combination. And why Mahalanobis? Because it can remove joint outliers and prevent truly missing. Also, it can improve robustness. So in this Mahalanobis mask steps, we use the sub-steps as below. First, grouping, and then statistics, and then parallel distance, then adaptive thresholds, and the last masking. And we got the result like overall anomaly rate like 1.59%. And in the Mahalanobis step, we moved all distance calculations from CPU to GPU with 3 main techniques. The first is CUDA kernel parallelism, and the second is multi-GPU trunk scheduling, and the third is local memory and regularization. Yes. And the mask merging result seems pretty good because these three tasks they are almost parallel, but they have something a tiny part in common. After masking, we interpolate, the most challenging part of processing because 160 million rows need features from different tables and 3 levels of calculation. The core flow as below, like 6 steps. And the GPU acceleration highlights for interpolation, like cuML nearest neighbors, Namba CUDA kernels, and the desk CUDA DF. Each kernel is a Namba CUDA function where each thread processes one record, avoiding pattern loops. This pipeline the 3 interpolation dimensions on the GPU with high throughput for large-scale spatial temporal data. Finally, we checked interpolation quality. We saw some mask flags false points got tiny changes because of multiple memory copies and GPU floating point noises. And 1,735 rows remained missing. Those had no neighbors in any of the 3 kernels, so we applied a second round of interpolation to fill those, then rechecked it to confirm no gaps. And next we build a model. This is the most familiar steps, starting model training from high quality data. So in this part, I wanna share the model architecture. It's not quite confused. It's quite simple, to be honest. There are 3 parallel heights for 5 minutes, 50 minutes, and 30 minutes, each with 2 graph siege layers and linear output to 1 value. And the training pipeline steps as below. First, data preparation. Second, subgraph sampling. The third, model optimization setup. The fourth, epoch loop. The last one is the validation and scheduling. And in this part, I also use some GPU accelerations for the performance optimizations. I used compiler library tuning, asynchronous data transfer, and neighbor sample for on GPU. And for the core compute flow, I also used the 4 GPU acquisition, multi-GPU parallelism, and mixed precision training. And all these GPU acceleration ways, they all help to train the model faster and faster. Then let's see the performance results. I used the 5 V100 GPUs, and the first one is the baseline one with 1 GPU no acceleration, and the second one is the single GPU with acceleration, and the third one is with multi-GPU parallelism and all the steps of acceleration, and we can see the differences among those 3 steps. And I also wrote a prediction script. You can input date, time, station ID, and flow speed, occupancy, and key. Key means the surrounding K stations, and it will predict the 5 and 15 and 30-minute flows for the station and its key nearest neighbors. Then draw line polites. For example, station 3939 on Sunset Hill Avenue at 2025 January the 1st in the point 0 with flow of 100 shows a clear upward trend over the next 30 minutes, while neighbors each show different patterns, some staple and some deep then raise. This demonstrates the model capture both topology and temporal features, though there's room for improvement. And overall the model is fairly simple, so there's plenty of optimization space. And I gained a great deal from this project, including data cleaning and preprocessing, large-scale training and acceleration, debugging, and initial software-hardware co-optimization. So finally, thank you for your attention, and I wish you have a great day.